Today in the Teardown channel, we are going to be analyzing a folding shelf bracket. Here are a couple of things to keep an eye out for. A loading of 500 pounds max, but where? How do I measure the torsional stiffness of the whole thing easily? What is the buckling force of the links such that they bow outwards? Hello and welcome to the Teardown channel. My name is Eddie. Today we're going to do something a little bit different, and that is we're going to analyze this folding shelf bracket. So the story behind this is I am in the basement and I want a temporary workbench. So I went and looked up the hefty ones, the ones that can take 500 pounds. I installed everything, and this is with the maple block that's about 45 pounds. And then when I put a weight on it, about the middle, I noticed that the table's just deflecting a little bit too much for comfort. And I'm like, this can't be how it works. And I go below it, and I'm looking, expecting something to have gone wrong with my anchoring to the wall. And instead, I see that these little links are just bowing outwards and buckling. And I'm like, wait, this is less than 100 pounds of loading, and they're buckling already. So I did what any proper geek would do, which is I created an experiment such that when I load it up, I actually measured the torsional stiffness of this to predict how much angular tilt I'm gonna get as a function of the force and where it is. And then I decided to go one step further. I decided to go and said, if I transfer a load that's axial here, that force is going to have to be supported by this little link. What does that mean? That means that this link is going to be under Euler buckling. So I went and did the analysis as well, and now I'm going to share with you exactly what I discovered. Welcome everyone. Today we're going to be measuring the deflection that takes place with this table when you put an object on top. The mechanism below says that it's rated to 500 pounds. However, once you go in there and you put even just, this is about 20 pounds, it starts flexing and the links below the table start buckling outwards. So I actually don't believe this is rated to that weight. When you look at it below, it's a little bit scary. So what we're going to do is we're going to measure it by using buckets of water. And we're going to put a laser here. And we're going to project the laser out into a wall and then measure the deflection that takes place with a given weight on it. Using that and with the known weight, what we're going to do is then try to reverse calculate what the actual properties of that mechanism below are, and to determine under what conditions is it actually rated for 500 pounds. This is reverse engineering 101 for actual things that you can actually find in your home. So I'm going to get started. A lot of it is going to be loading up the laser, projecting, measuring that deflection, and then we're going to go and do the analysis behind this. There's a line here that's scribed to where we're going to load the center of the buckets. This tape is going to allow me to put another bucket on each side such that they're centered on the line. That is 23¼ inches away from the back over here. And then to the tip of the table is 30 inches and a quarter. With the laser mounted here, what we're going to go do is going to pan over and we're going to mark the 0, 0 location. So right now, it's going to go right there, and that is origin. And what we expect to happen is, as we put more weight, this point is going to go down due to Abbe error. Let's start. Point 1. Data point 1. First, we're going to put one bucket right on the center of that location. And mark the point. 1 bucket. Now we're going to move on to 2 buckets. So make sure that the buckets don't apply a torsional load on the table. We're going to put them roughly at the center each. Hold up. Am I missing something? Or did I hit the laser? I put the laser to the side. So we're going to have to start over again. Oh, no, it's there. It's aligned. So the laser just moved when the bucket's there. So as long as it stays vertical, there's one way to determine. If I move this back out, does it go back to the original point? Yes, it does. So just have to be careful, don't move your sensor. Don't pick your sensor. A little bit off, it's about 1 millimeter off to the side. You'll see. So with 2 buckets, we're going to go here. Two buckets. Now we're going to do 3 buckets. Let's try to make sure not to touch the laser again. 1, 2. Third one. Come on, B. 3. So now we should have 3 buckets here. Now we're going to go 3 buckets and 1 ring. So let's remember that each bucket is 7.8 pounds and each ring is 9 pounds, 9.5 pounds actually. So now we have 3 buckets and 1 ring. Now we're going to go 2 rings. 3 buckets, 1 ring. Now we're going to add the second ring. Alright everyone, so we actually have done our loading, our experiment. The unit actually went back very close to the point of origin. There was a slight lateral shift. It was basically the 1-2 millimeters sideways when we went from 1 bucket to 2 buckets, and it actually moved the laser a little bit, but everything looks like it's aligning well. So what I've written here is the vertical displacement as we added the 1 bucket, 2 buckets, 3 buckets, and then the rings as well. So as we loaded, that angle started to deflect. And this, based on the distance, now we actually have what the Abbe error will be. And from that, we're going to go try to back calculate what the actual parameters are for this configuration. And eventually, what we're going to try to get to is trying to reverse engineer the conditions that they are actually claiming that this mechanism is rated for 500 pounds. And so we're going to weigh everything out, do the analysis, and then we're going to see, hey, this is how close it is, or under these conditions, this is how it's going to work. This is all about just having fun, reverse engineering in your garage, okay? So we're going to keep going. So this is underneath right now. The table is completely unloaded. What I'm going to do is I'm going to show you what the deflection is slowly. This is 1 bucket. Now we're going to add slowly the 2 rings simultaneously. So it's going to be 1 bucket and 2 rings. And just look at the deflection that's taking place in these links. And now I'm going to add the 2 additional buckets. So it's going to be 3 buckets and two rings simultaneously. So let's get the analysis going. This is the total length that we have from the pivot location all the way down to the projection plane, the distance to our applied load, and our applied load in newtons. So using those values, I calculate a total torque, which is based from the load and from the static load of the table, the thing that doesn't change at all. And then I use the displacement here to calculate what the rotation angle is about the pivot location. And it calculates in radian because it's the arctangent of delta P over LT. And then so I convert it into a degree units. And then from that, we use the torsional stiffness, which is basically, here, this should actually be torsional stiffness. So that's a torsional stiffness, which is the torque divided by the rotation angle. And in reality, the way that we're going to want to use it is to say, hey, given this torque, what is the angle that you're going to have? And as you're going to see it way after in one of the bloopers at the end of the video, it's you put a little bit of force and it goes and bends significantly at the end. So that's a dynamic system as well. Let's get started. Folding shelf, let's do the analysis, okay? This is so big, let's convert it into that little cute thing. And actually I like playing with Legos, and that's the only reason why I did it. Simple. Alright, before we start, we're gonna go barbaric. I'm gonna set up our working digital table. Ta-da! How do you like this for digital? In the age of technology, I go paper and pencil. Okay, actually it's going to be more to say markers than anything else. Alright, on the serious note, so one of the things that we're going to try to do is I'm going to try to help you set things up for any problem. So here's the method, and I put it on the little folding little thing so we can do our problem here and we keep our method in mind. Before you begin, you have to have a coordinate system. Do not go home or do not start a problem without a coordinate system. It just doesn't go well for you. Okay? And then the next thing we're going to do, we're going to label components. Okay? And what I would love to just put everything here already. I like playing the game, show me the rule for the next one, show me how to do it, and then keep going. But don't just give me everything out and then go for it. If you want to know what it is, first we're going to label the components. Basically, hey, this is this part, this is this part, go to the points, do the sum of the forces in the x, the sum of the forces in the y, the sum of the moments by establishing equilibrium. But let's just go step by step instead. Label components. Hey, look, it does a really good job being a little support member. So, where's the printout? Here's the printout. Ta-da! So, this is the model. We're going to call this a bar and support. And let's remember, there is a force somewhere along here. So let's start with the bar. The bar goes there. It has a point A. There's a point B. And I don't know if you can tell that, so let's start using bigger. A and B. And then let's get this guy here. And then this is O. And this is B. Okay. That's labeling components. Is it? Now let's put our forces in. So, point 2, forces. this is our applied forces as well as our reaction forces. So we're going to put a force F here. F star. And we're going to try to figure out how F star translates to a force on this support. So at point A, because that is a pin joint, we're going to have only force. I usually do face direction, okay? So in this case it's not a face. A, comma, in the X, and F, A, comma, in the Y direction, and the same thing we do here. F, B, in the Y direction, and F, B, comma, in the X direction. Now here's a fun part. You can say, how did you pick the location of the forces? How do you know they're both in the positive X direction? Here, see, X, Y. Let's start with the coordinate. How do I know that both of them are in the positive X direction? I don't know. This is actually just the method. The method will help you determine which direction is which from later on the math. Pick one, go with it, okay? So let's go here. Because point B is joint there, it's equal and opposite, okay? So we're gonna put another force here, equal and opposite. F, B, comma, X, equal and opposite. F, B, comma, Y. Now, you can say, well, why are you putting it the other way at point O? Look, if it's new, I'm going to put it in as in the positive direction. And then just, we're going to analyze them on their own. 0, comma, X, F, 0, comma, Y. Forces, applied force, great. Next. Sum of the forces in the X, sum of the forces in the Y, and the sum of the moments. So forces, now equilibrium. And what does this mean? This means, if you see me humming or something, it's because I am actually listening to music while I do this. Why? Because that's the way that I usually work. I like music, and it helped me dance with the problem, to say the least. So let's do this. How do I do this? Look, I have some of the forces in the X. Ooh, let's do that. Sum of the forces in the X for that equals 0. Therefore, F A comma X plus F B comma X must be equal to 0. What does that mean? F A comma X equals negative F B comma X, right? Done. When I get this, I box it. Now let's go to the sum of the forces in the Y equals 0, because it's all equilibrium. Otherwise it would be F equals ma, because it's moving. In this case it's not. Ooh, look, we have 3 forces in the Y for this one. So force A in the Y plus force B in the Y. Why did I put that F in the minus? I could have put it in the positive. Doesn't matter. I can just put minus F star equals 0. What do I really want to find out? Okay. In this case, eventually I want to just get a system of equations so I can find force B. And this force B is going to get back up here. So let's just put F of A, Y. F of A comma Y has to be equal to, that's this force, F star minus F B comma Y. Okay, I can dance with that. Why am I doing all of this in these, you know, letters versus numbers? Because this is going to help me do it for any system eventually. All right, let's do it for another problem here. Eventually we'll do this some of the moments. La 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 la. Let's put you up there. Yeah, let's just do it for here. Sum of the forces in the x for you. What is that gonna equal? 0. And in the x, ooh, we have this candidate here, minus fb comma x. Why? Because equal and opposite of that one, but that means this is in this direction. That makes equal 0. So f0 comma x equals fb comma x. Closed. Ooh, we're getting somewhere now. Same thing, some of the forces in the y. La, la, la. What does that equal? We're getting used to this. Oh, by the way, be careful when you get comfortable like this and just singing along with it, that you don't accidentally get the sign wrong. I've done that plenty of times. Or that you miswrite a letter or a number here, and then that goes really wild. Okay, so f0 on the y minus fb comma y. And I did this throughout college. I always used to put my finger, oh, you're next, oh, you're next. Okay, so what does this mean? f0 comma y equals fb comma y. By the way, this is one of the most useful pieces of advice that I will give you. Keep your work really clean. If you don't keep your work clean, it is going to be a headache for you in the long term. Okay, we have equilibrium. Now we're going to go sum of your moments, which is part of equilibrium, but I wanted to put it in to its own accord. So what is a moment? Moment is defined as R cross F. And as soon as I start writing this, it's going to be an abstract Vulcan language, and I try to hesitate saying Vulcan because some people may actually speak Vulcan. So then I thought about, hey, what can I say about Avatar language, right? And then it was like, wait, no, some people may speak the language from a planet, which actually was really kind of cool that they created their own language for it. So let's go and start this is a mini lesson on moments. And let's make this point P. If I take the sum of the moments for P, right? What is a moment? A moment, it needs a lever arm. Okay, so we're gonna call that L. And then a force. What's the force? That force could be, if it's that way, right? That's a force. So what's the moment? This little cross product means give me the 90-degree component of it. So if it's this pink one, this force, that means 90 degrees is this one. So it's whatever this component that's 90 degrees, orthogonal. Okay? So whatever it is, then you locate it by the angle, and then that's what it goes. That's all that cross product goes into. So in this case, the way that I've done it is I put all my forces in the x and in the y direction. Therefore, we'll figure out the angle stuff later. Let's start with the sum of the moments here. You see how f of b in the x direction is aligned, and f of by in the y direction is 90 degrees. That saves us the hassle of the angle. And it's not really a hassle, it's actually really easy. So let's look at that one. If I go and I pick the sum of the moments about A, then I have an entire system of by and f causes a moment. If I go the sum of the moments about B, then that means fay and f star causes a moment. So you just have to pick one. So I'm going to go the sum of my moments. And then this is what we call the bar, right, of A has to be equal to 0. What does that mean? Okay, so that means I'm at this point, and because there's no lever arm, you go away and you go away. We have none of that. Now, if I go here, because f of by, there is no orthogonal component, that means, oh no, f of bx, sorry, there's no orthogonal component, that means that goes away. And now I need the length from here to here, LB, and then I need the length from there to there, and we're going to call that L star. I don't know if you can see that. Great. So length LB multiplying times right hand rule FB comma Y, and then this is right hand rule going down, L star L 0. So what does this equal? That means F B comma Y equals, now that swings over to the other side, L star divided by LB times F star. Dun, 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 dun. That means we have something here, and now let's do the same thing, and we'll probably do it in a different color just to vary it up. By the way, this reminds me of a story that I like using colors. Sometimes it's good, sometimes it's bad. And I failed my qualifiers exam the first time because I got too enamored using colors and not enough focusing on the content. And then it was like, oh, so what does that mean as a lesson? Hey, guess what? Focus on getting the job done right before you just start going and having fun. So let's get to this. Sum of the moment, about 0 on the support component is going to be equal to 0. Now check this out. This is going to be, let's put it HB. That's the height going from here to here. And if we get the real one, that's this height, and this is that other length, LB. And then the force is here, so that's going to be that L star. Okay? So that's HB. And then we also take this, and then we already know that this is LB. Hey, L is for length. B, H is for height. Yeah, how intuitive. So even as I write things down, I have to go with this. So sum of the moment about 0 equals 0. What does that equal? Equals length. This is HB multiplied and R cross F, that's in the positive direction. F B comma X. Ta-da! Now give me the other one. LB. LB times FB comma Y. It has to be equal to 0. Hey, what's the sign? L F. Negative. So what does this mean? Now we're going to get the other one. Okay, I have a bunch of equations now, but check this out. Now I have an FBY, and then if I have this FBY, that means I have this FBX. Ooh. I'm going to start getting them all into FBYs, and then get this out, and then, hey, this I can relate to that, and start breaking everything apart, okay? Eventually, what I want to know is the forces FBX and FBY, or FOY and FOX. Why? Because this is going to give me the amount of compression or extension, right? In this case, I know it's definitely going to be compression of the support component that's going to cause it to buckle and distort. So FBX, F B comma X, that's going to equal to LB over HB. Great. Right? You move that to the other side, and this is going to be FB comma Y. Ta-da! Great. Now we have a challenge. And here's the challenge. I've run out of paper. Alright, so system of equations. I have 1, 2, 3, 4, 5, 6. And solve it. So what are we actually looking for? We're looking for this compression. If we're looking at this, I need to know FB of Y and FB of X. FB of Y and FB of X. Hey, FB of Y is a function here, but I know that, and then that gives me in terms of L star and F star, and a known length. So this goes in here, and I can actually solve it based on these two. Now, why did I do the sum of the forces in the X and the sum of the forces in the Y? Because if I want to do the reaction forces here, which eventually you do, especially for more complex problems, you just get used to the method. Sum of the forces in the X, sum of the forces in the Y, equilibrium, which is there, some of the moments, and then you'll get all the information that you need. If you want to do cheat sheets, or like if you're going on doing your qualifier exam, fine, you can jump up to here, but this comes only with experience, okay? And what I'm going to do is clean the board and go to the next one. So there's the 6 equations on top, and we're just going to do this section here. And I gave myself that spot up there just in case. So if F of B in the Y equals L star LB times F star, and then that means that goes in there, so F of B in the X has to be LB HB times L star over LB. Right, you're seeing why I put it here. LB HB times FBY, but FBY is here, so it's L star over LB times F star. Ooh, check this out. You go away, you go away. And now we're left with F, B, comma, X, okay, equals nothing more than L star over HB times F star. Woohoo! What does this mean? We go to our good old friend Pythagorean. I have two forces. I have force in the X, and this is just generic, force in the Y. What is the magnitude of that force? Whichever way it is, that means that F equals the square root of Fx squared plus Fy squared. Oh, I can do that. I have an F of B in the Y, F of B in the X. Square both of them. Let's call it a day. So let's put this in. It's going to be F star. So that means this is going to be F, and remember, this is the support, is going to be equal to, and I'm going to just move a little bit on the math and bypass quickly. I'm assuming you can do this too. It's going to be F star L star, because it's common to both of them, times the square root of 1 over L B squared plus 1 over HB squared, right? Because if I put this inside and I multiply, that means F star L squared, that's all there, and this is F star L squared, and that means that's all there. Wonderful. And this is what we're going to put into. Now, where is that going? That's going to go for Euler buckling. This force cannot exceed F buckling. So we're going to transfer this support force into a buckling force and see what is causing this component to essentially buckle outwards. In order to do that, we need to start a brand new sheet of paper and introduce everyone to Euler Buckling 101. Next slide. Ta-da! So, by the way, this is one of my favorite engineering reference guides. I use this for the PE exam in mechanical engineering. And let's get us here. Euler Buckling 101. Here's an equation. These are different modes for the pin joints, for the built-in ends. So what I'm going to do is instead go over what the equations are and then actually just put it all in an Excel spreadsheet and look at the numbers. Okay? So this unit is rated according to them. And let me zoom out to 500 pounds, and that's both of them. So it was like, oh my gosh, when I did the test on it and I even put it, I was like, there is no way this can take 500 pounds. Absolutely no way. But my job as a geek was to say, Eddie, so tell me the conditions in which this will take 500 pounds. So I started with this force of the support, right, and that's going and compressing, and I said, okay, let's do this. So if that's the support, what do I know from the other side? F support has to be equal to Euler buckling, and Euler buckling is just another equation. E, which is part of the material properties, A, which is the cross-sectional area of that, and then it's divided by this funky looking number. And this funky looking number is CL divided by K gyration squared. So you can start going, oh my gosh, this is getting difficult. No, it's all just apples and oranges and just the same thing, just have to keep it. So this K gyration is actually just a square root of I divided by A cross-sectional. And that's the same cross-sectional area here. And there's the Euler buckling takes different forms. And this I equals just simply 112 BH cubed. So, oh, that L here, this is L of length. So that L is the L of the length right here. The height is actually the thickness. So that height is the thickness of this component. That B is the width here. And anything else? No. Oh, that C factor. So that C factor comes in whether you are pin joints, which equals to C, let me go back to that reference, of 1, or, let me remove this guy out of the way. It's either 1 for this configuration, or in the other configuration where it's built in, and I actually believe that this is not built in for this system because of how it's actually deforming, and also because of the clearances, and this is C equals 0.65, but because that C goes in, there's going to be a factor of about 2.36, or actually we can round it up to 2.4. Alright, so that's what the Euler buckling goes. So we can configured that equation into find this L. What is that L star? If you remember from the initial one, that L star was, if I have this, L star was the location from the back where I apply my force, my critical force. And in order to make sure that we get everything aligned, if I want to put that F star from the load of the machine total, the load of the mechanism total, that means I have 4 links total, 2 on each side, and then 2 units. So this is where you actually get the math correct. That you divide that quote-unquote 500 pounds divided by 4, that's how much each link can take, and then do the analysis for it. So that's F star. Let's get back to this. Now we just reorient this equation and say, okay, L star is equal to, this is pi squared E of the material property, so you can actually assume that this is stainless steel. A cross-sectional area, which you know that the cross-sectional area of this is this width times the thickness, divided by C, which is equal to 1, L, which is the length from here to here, and because I catted the unit, I know that length, divided by gyration, square root of I, so it's going to be 112 h cubed, we'll make that a b h cubed, okay, and 12 a again, which is the cross section. And look, I don't expect to do this by hand. This is why we're going to use Excel spreadsheet. I do this by hand to see what the power factors are, okay? And then that goes to a square, that's a 2. Let's keep everything in friendly. And then if I want to make sure that that is the F star total of 500 pounds and do it, I'm going to put F star divided by n links, which is 4. So that would be the 500 pounds, but make sure to convert it all into the same units. So if you stay in newtons, make sure that everything is metric. If you stay in English units, stay in everything in English units. Okay? Don't mix all your different species of it. Divided by 1 over LB squared plus 1 over HB squared. It is probable that I may make a mistake on this. So what I do is I like to double check. E pi squared EA CL. Did I convert this correctly? A cross-sectional is here, 112 BH cubed, check. All of that is in the squared. Now, because I'm dividing it, F, I adjust for the number of links, so that's in the total. And this parameter. Now, I went ahead and I did that in the Excel, and here's what were the results. So if I assume a pinned joint, right, that's this one, that means C equals 1. The buckle, if I were just to do the analysis, F buckling per link is roughly 374 newtons, and you can divide that by 4.45, and that's going to get you your force. That means that L critical, if I want to withstand 500 pounds is just 2.56 inches away from the back. So here you go. On your mechanism, that means here 2.56. So fine, it can be rated for 500 pounds, but only 2.56 inches from the back. That's your center of mass. And that includes everything: your weight of your machines, your weight of your microwave, everything. And the table as well. Now, if I assume that this is the other configuration, which is fixed, right, then that means C equals 0.65, and this is the built-in. That means that this buckling force pushes to 883 newtons, and I can have that at L critical at 6 inches from the back. That's cute. But actually, you know, if I have this, and let's turn this around, 2 inches, 2.5 inches is right here. I'm not putting all the weight out over there. This is a table, for God's sakes. I'm going from here to here. So what if I were just to go 10 inches, right? I want to put my force, this is a 20-inch component. I want to put my force roughly at this mark, or this pin, right? Which is about 10 inches. What does that look like? And this is where I got a little bit on the because I went on the pin joint and I was like, okay, if my L star is 10 inches, the maximum weight that I can have in this pin configuration is 128 pounds before it starts buckling. Oops. Let me move back a little bit. And then if I make it to be 10 inches, and I assume that it's a built-in configuration, this is 300 pounds. So this is kind of weird, because this says, they tell you that it's 500 pounds of force that this can take the entire mechanism. However, yeah, it can take 500 pounds if you load it up all the way back here, right? Or if you assume that the configuration is such that you load it up all the way about here, and in the best case scenarios. The truth is, I'm going to load it up about here, about halfway, right? It's a 20-inch table. I'm not going to put all my weight back there. It's a microwave. It's 2 microwaves, whatever it is. So it's a little bit misleading to believe that this can actually take 500 pounds in the regular user configuration. And if you were to ask me, fine, it can take 500 pounds, but you have to put it all the way here. And the user most likely is not going to put it there. In my setup, when I have it downstairs, I was going to put it right about the middle, right? I wasn't going to put it all the way out there, but the weight was going to be about here. By the time that I put my little bandsaw, my little table saw, and I put some loads on it, and including the table, this is going to start buckling. And that's actually what's happened, is these components are starting to buckle. And I don't feel comfortable using them, because you can see what the difference is. And you can see them downstairs later on the video of what's happened. That as they start and you put a load, they start separating. And what I fear is that there's going to be a prying action on this component, on the pin, and then the pin's gonna fall out, and then the whole table's gonna fall down because there's not gonna be any support. The pin's gonna go away. So here's the analysis and the numbers. I put all of this stuff in an Excel spreadsheet, so you can go ahead and find out the numbers yourself. If you find anything wrong in the Excel, by all means, please let me know. But this is, yeah, fine, it can take 500 pounds, but the buckling force will actually kick in after 2.5 inches from the back. and after that it's going to start plastically deforming, leading to a failure in the system. This is the Excel spreadsheet that I created, and look, at first glance I know it looks overwhelming, but let's just dive in little by little. So this is the geometry that we used in order to actually do the force equilibrium, and we use those variables here to calculate the axial force per link. This is the geometry of the actual folding shelf bracket. If we were to want to change the materials, here's a materials table, and then that is just a drop down list here. And this is the end configuration, whether it's both ends pinned, both ends built in, and this is another table that just gets used in there, like a drop down list, and it references this table. And this one is the column geometry. So when we're going to go put the width of it and the thickness of this element that's buckling, this is where we do it, and it just comes in as a drop down list here. So let's start jumping into the actual table. I go first and I look at, okay, what, as a user, I'm going to put an applied force here first. So what is that applied force? Okay, so it's about 300 pounds. And I write everything in newtons and then I convert it to pounds for other people's reference. I try to work everything in metric. And then the location of that applied force, roughly 10 inches from the back. Number of links 4. This is the downward force per link. And you can go through it, and what I did is I put the axial force per support link, and then that is based on this applied force. Now if I were to just look at the analysis and say what's the maximum load that this is rated at, and then give me the critical length, we're going to use that in a bit. After I have my loading requirements, then I actually go into do just an independent buckling. What's my material? I can change my material from aluminum to stainless. I'm just going to go stainless. That brings me all of these parameters. This is just my using from my properties tables. If I want to go and I change my built-in configuration, both ends pinned, and it changes my constants for buckling. Or if I want to go from recommended to the ideal parameters as well. So I go there, and then this tells me which buckling constant is the one that's active. The critical length of the buckling is actually this length right here, the length of that link. So that I set it based on creating the CAD measurements. Column geometry, this is what references that other table to the right. And then that goes into rectangular solid, and this will pull the area moment of inertia and the cross-sectional area. If I want to override it, then I just go click yes here, and it's going to override it to these two parameters in yellow. So if it is in yellow, that means that's where I put values in. If it is in white, just leave it alone. If it is in this peach color, that means it's a drop down. And then this will actually tell me which parameters are active. And I go and I do the slender ratio test, and then you can go and read about it a little bit more. I put comments here, and then I also put the axial force to buckle, and that's what this value is. So if I have it in the existing geometry, both ends pinned, stainless steel, the axial force to buckle that component is 373 newtons, and it calculates the stress as well. Now, if I want to actually go and say, if I have 500 pounds, where will those 500 pounds be in order for this not to buckle? And this is 2.5 inches from the back, 2.6 inches from the back, and that is if both ends are pinned. Now, if both ends are built in, it's 6 inches from the back that I have to go to be within your center of mass, and that includes the table as well as any component that you're putting on top, and that's the max. If you do both ends pinned, which is what I believe this mechanism is, because otherwise it's prying and you have tolerances in there, you don't have by Saint Vinay's the setup in order to actually hold the both ends fixed. It's actually both ends pinned. I go up here and I go, okay, I have 300 pounds. 300 pounds, I'm going to put an applied force roughly at 10 inches. Okay, I have 4 links. This is fixed because that's what the setup is based on that unit. Is it going to buckle? And so you compare this axial force, the 880 newtons, to this force, which is 373 newtons, and that means that the axial force to buckle is exceeded, and this is going to break. So the other option is, let's say you divide this equals divided by 3. So now I have 100 pounds, and at 100 pounds, that means that's 293 axial force on the link, and that means that my buckling is 373 because it hasn't changed. So that is almost what, 80 newtons off? Yeah, 80 newtons off. So it is 80 newtons off from buckling. So I can withstand about 100 pounds total, and that includes table and everything, about 10 inches away. And that's what I would actually be comfortable loading this unit at about 100 pounds total without those links buckling. However, if you have eccentric loads, this doesn't take this into account, and that actually adds an additional complexity to the system. How about those 500 pounds, huh? It's 500 pounds only if it's loaded about 2.5 inches from here. As a user, I'm actually going to be loading it up about 10 inches from here, so it's not really 500 pounds, it's much less. And what you saw as well is that even under 100 pounds, these are starting to spread out and buckle. There's a couple of fixes to it. That is changing the geometry of these links, and remember that it goes like the thickness cube. So that's one way. The other way is, hey, I have to use this, so what do I have to do in order to actually make it feel safer, at least for me? And I'm applying engineering reciprocity. So flip it 180 degrees. Bloop. What's the difference? The difference is that under this condition, these links are in compression, hence Euler buckling. However, when I flip it 180 degrees, these links are in tension, which is a whole different failure mode. And this mechanism on its, just by flipping it 180 degrees, now it's going to have its own different failure mode characteristics. However, that failure mode characteristic will be based on tension of these elements and also the strength of the links, as well as the back support of being able to withstand the moment applied by the load. A lot in this little simple mechanism, and I hope you've picked up a couple of the tricks of how I look at designing an experiment, how it goes into doing some of the just analysis, Euler buckling, and just the approach in general. Again, thank you for watching the Teardown channel. If you have any comments, leave them below. I'll try to get to them as soon as I can.